Hello, I welcome you all on Saswat Prawa. I'm here with my new video on materials. So every product you see around you, a car door, mobile phone frame or aircraft wings, medical implant, even a simple screw, that all made up of metals, only as good as materials used to make it. So, but here is the interesting part. No company trusts a material by simply supplier words that supplier says, yeah, the material is so strong. They need proof, real scientific measurable proof. And the proof comes from material testing. Before a material become a part of real product, it goes through a long journey of tests like mechanical test, thermal stress test, fatigue life checks, microstructure study, corrosion test, impact hardness, fracture, toughness, and many more. Because one failure can cost millions or even lives. So today we are going to explore how companies test new materials, why these tests matter, and what engineers, researchers, and students need to understand about the science behind them. Let's begin.
You ever just look around and wonder why why it all just works? I mean, from the chair you're sitting in to the screen you're looking at, there's this entire hidden science dedicated to making sure things don't just fall apart. And the secret? It's all about breaking things on purpose. So let's pull back the curtain on the incredible world of materials testing.
Seriously, just think about this for a second. You see an airplane wing flexing like crazy through some gnarly turbulence, but it almost never, ever breaks. How is that even possible? Well, I can tell you it's not magic, and it's definitely not luck.
The answer is testing. Rigorous, relentless, gotta know the answer testing. This whole science of breaking things on purpose is really the invisible backbone of our modern world. It's what keeps aerospace alloys safe, what informs your car's chassis design, and it's in the steel used for buildings and bridges. It's even crucial for the battery pack in an electric car.
Okay, so where do engineers even start? It all begins with the most basic fundamental questions you can ask about any material. Just how strong is it, really? Let's get into the fundamentals. This is what we call mechanical testing. It's pretty straightforward, really. It's all about applying a very specific, controlled force to a material so we can measure its core properties. We're talking about its raw strength, sure, but also how stiff or flexible it is, and its ductility, which is basically just a fancy way of asking how much can it stretch or bend before it finally gives up and snaps. And this right here, this is the beast that does all the heavy lifting. It's called a universal testing machine, and its job is brutally simple: to pull, push, and bend little samples of materials with an incredible amount of force. It does all of this just to find that one single, crucial piece of information, the exact point at which it fails.
And believe me, this principle scales up in a huge way. That simple little diagram of a bend test on the left, it's the exact same idea as what you see on the right, where this massive machine is literally crushing a cylinder of concrete to test its strength. No matter the scale, the goal is always the same. Apply force, measure what happens.
But, a slow, steady force is only one part of the story. The real world is full of sudden, sharp impacts. So, how do we test for those?
And that is the next critical question, right? What happens when a material has to absorb a massive amount of energy in just a fraction of a second? Think about a car crash, or even just what happens when you accidentally drop your phone on the pavement. To figure that out, engineers have a pretty clever method called an impact test. The concept itself is beautifully simple. You take a heavy pendulum, you lift it way up, and then you just let it go. It swings down and smashes right through a small, notched piece of the material you're testing. And here is what that actually looks like in a lab. It is, for all intents and purposes, a giant, perfectly calibrated swinging hammer. By measuring exactly how much energy that little sample absorbs before it shatters, engineers can get a number for the material's toughness, its ability to stand up to a sudden shock.
Now, it's not always about a material completely breaking apart. Something closely related to toughness is hardness. This is all about resisting surface damage, scratches, dents, and general wear and tear. And that's absolutely vital for things like the tip of a drill bit or the outer shell of a protective helmet.
Okay, so we've pushed, pulled, and smashed these materials. We're getting a pretty good idea of what they can handle. But to truly understand why they behave the way they do, we have to go deeper. We need to look inside.
We're talking about something called the microstructure.
The best way to think about it is like a material's internal architecture. It's the unique pattern of its grains, its crystals, and all the tiny little imperfections that are totally invisible to the naked eye. This hidden inner world is what gives a material its true character.
And this, get ready, this is what regular old steel actually looks like when you magnify it 5,000 times. See? It's not some solid, uniform gray block at all. It's this complex, almost beautiful landscape of interlocking grains. And every single material, from plastic to ceramic to metal, has its own unique internal fingerprint just like this.
And this internal structure is everything. On the left, you see a really well-formed, uniform microstructure. That's what gives the material its strength. But on the right, you see something different. Those little internal cracks, those tiny pores, those are the weak spots. They are the exact starting points for a catastrophic failure. Understanding this difference is the whole key to making stronger stuff.
So a material can be strong, it can be tough, but can it last? I mean, really last? The next set of tests are all about simulating years, sometimes even decades, of real-world use and abuse.
Let's start with a really simple idea we've all experienced. You take a paper clip, you bend it once, no big deal. But if you bend it back and forth over and over and over again, it'll eventually just snap, right? Well, that weakening from repeated stress has a name. It's called fatigue. And it is one of the most dangerous and sneaky causes of failure for anything that moves or vibrates, like bridges and, yep, those airplane wigs.
So, what do engineers do? They build machines, like the one diagrammed on the left, that do nothing but bend, pull, and twist material over and over again, sometimes for millions of cycles. All that data gets plotted on a graph that looks like the one on the right. It's called an SN curve. Now, it might look a little complicated, but it tells a very simple story. The higher the stress you put on it, the fewer cycles it can survive. This little curve is incredibly powerful because it lets engineers predict, with amazing accuracy, just how long a part will last before it's in danger of failing.
And of course, you can't forget about the environment. That's where these special chambers come in. They simulate years of exposure to brutal sunlight, salt spray, crazy temperatures, and humidity. It's how we find out if the paint on your car is going to fade after 5 years, or if the plastic parts in your dishwasher will get brittle and crack after a decade.
So, after all this, all the pushing, pulling, smashing, and aging, what's the big takeaway? Well, it really all comes down to understanding one single thing: failure. Which brings us to the most important question of all. Why? Why do we go to all this trouble to meticulously break things in a lab? What's the point?
Well, it really boils down to this. We test to find a material's absolute limits long before they could ever be reached out in the real world. We test so we can see that invisible, hidden world inside the material's microstructure. And most importantly, we test so we can learn from every single crack and every single break so that we can design things to be safer and more reliable for all of us.
Look at this. This isn't just some random broken piece of metal. This is the face of a fracture, magnified 400 times. And to an engineer, this surface tells an entire story. They can read it like a book to see exactly how the material failed, where the crack started, and how fast it grew. It's basically a roadmap for how to prevent the next failure.
And that really is the heart of it all, isn't it? It's a simple idea, but it's incredibly profound. To build things that last, you absolutely must first understand exactly how and why they break.
Materials are the foundation of every product we rely on. Let's get an example of material of bearing that is we use in a simple bicycle, or similar kind of bearing we used in aeroplane. So the material of the bearing should be that strong, so we rely on. So behind each material like steel, aluminum, polymer, composite, and ceramic, battery electrode, there are years of testing, validation, and scientific analysis before it ever reaches a factory. Mechanical strength, heat resistance, fatigue life, microstructure, corrosion behavior, all of these determine whether a product will succeed or fail. So next time you see an aircraft take off or your phone survive a fall, remember it's not a luck. It's the result of deep testing and smart engineering. If you found this video helpful and you want more videos like that on material science, manufacturing and R&D and other quality tools, so don't forget to subscribe and stay tuned. Your life journey starts here. Thank you so much.